Sounds good.
just so that you guys can see this. Don't do it right now. But there's this spot down here on the calculator above the plus sign that says mem. And don't do it right now, but if you hit second plus sign, there's a place number 4 where you can go clear all the lists at once. So clear all lists. And then when you go back into your list, they'll be nice and clean. So there's a way to do that all at once. Second plus 4. Anyway, so hold on, I'm just gonna do this real quick. You guys talk about your plans for the day real quick. Oh no. Why isn't anyone? Mrs. Talbot, you're typing it in L4. Okay, back to the beginning.
Like, how are you gonna handle all of it? How are you gonna handle okay, but you can't say she's not good. You can, okay. She's probably not. No, Janet. She just. Because like, no, sometimes people are not. She is also like, I like smaller people. It takes less time to
Okay, guys, thank you so much for giving me that time. Okay, so the first thing we're going to do, although isn't on there. So once you have this situated, just scooch this to the side and then notice this entry that you wrote, see computer regression output resource page. So that's in your packet. And it says regression output notes at the top. Okay. For the few of you that forgot your packet today, you probably just want to hold on this and watch the video later and write it in. But just watch for now. Okay, so this is software output. So I have to be honest with you, I was just giving you a hard time about, your trusty TI-84. But, a 40-year-old dude at an accounting firm isn't going to have a like TI-84 hanging out in his backpack in his briefcase. He's not going to be like on a plane winging out his TI-84. Yeah, like my, 50-year-old ex-husband, when he's doing his regression graphs, he's just like scouring through the desk for a TI-84. Gotta be honest with you, that's like a high school and college thing. And then once you get to industry, you use software. Excel will do a lot of this stuff for you. Google Sheets will do some, Desmos will do all of it, although the older crowd won't use Desmos either, that's another education tool. But, when you see regression output, you should be happy. This means that somebody else did all of the work of entering in all the data values for you, and they did, linear regression on the software, and that just spits out the end result. So what you need to know is how you read it, because there's a lot of extra stuff on here that we don't use. So we're just going to be labeling things on here and kind of practicing some of the things that we learned this chapter. So the first thing that you need to know is that there are some words over here. Constant tells you the y-intercept. Let's talk about why that makes sense. What number is the constant in y hat equals a plus bx? Let's write that down here. Y hat equals a plus bx. Which one of those things is constant? A. Right. So this is telling you what the y-intercept is. So this number is A. And we don't ever use this. And I'm not going to cross these four out, but you won't know what these things are until second semester. So we're just going to limit our scope on this particular page for now. Okay, now time. This is great. It tells you two things. This is the slope. But it also tells you that time is the explanatory. I just wrote that because I was going to write X. And what I mean by that is it tells you which variable would be the X, and then this one would be the Y. Okay, so let me review. The constant is the y-intercept, which is this number, which is right next to where it says constant. This is the slope, and this is telling you what the explanatory variable is, or the X. And so you can go into your context and label which one's X and which one's Y. Okay, so our line of best fit for this particular situation would be y hat equals 1.79 minus 0.21 X. Any questions about that so far? Good. Okay, now we're going to practice some stuff. So, very important things we've learned this chapter. We're going to practice these sentences. Okay, the slope sentence. Okay, this is the slope sentence. B is the slope. For every increase in one X, we predict an increase or decrease of slope Y. Okay, now here's a problem. They really didn't tell us what units of time. So we're just going to say 1 time. So for every increase in one x, we predict a. Okay, now here's your next decision. So we predict, we have to decide if it's increase or decrease. What is it in this one? Decrease. Okay, y-intercept. Y-intercept is a. At 0x, we predict a y. At 0, what's x? Even though it's awkward, time. We predict what? Hmm? We predict a. What's a in this problem? 1.79 happiness. Okay. Next thing that we need to know is how do we get R from this problem? Correlation is R. How do I get R from the regression output that they gave me? Oh, well, you can, but I'm looking for it in words. What do I do? This is not supposed to be challenging question. Yeah, I heard it. Somebody said it. Square root R squared. Woo. Okay, now I'm violating something here that I hammered in my math kids, and if you don't know it, I'm gonna be really upset. What did I violate here when I square rooted both sides? I forgot something. Plus or minus. Okay. And this particular problem, you can identify whether or not it's positive or negative R though. Which one would this be? Negative, right? Because the slope is negative. So because it's going downhill, and we said that it was decreasing, then you know that it's negative. So you're actually going to have that moment of thought where you throw that in. Okay, so now we can write a correlation sentence, kind of. Okay, so 0.62, strong, moderate, or weak? Moderate. Okay, there is a Okay, so why did I put that question mark there? So if you don't remember how that sentence goes, you probably don't, and it's not your fault. Here is the sentence. Here's my question mark right there. Okay, now look back at the sentence. Linear, right? Okay. Do I have anything on this paper that indicates the form of this particular graph? Can I tell the form from numbers? No. Okay, there's only two ways to tell the form. Does anybody know the two ways? They're both pictures. Scatter plot or residual plot, what we learned yesterday. That's it. So remember how I told you I was like hesitant to give you like a scale for R? That's because a lot of times people just go to the numbers and they don't actually think about what shape is it. So I just put a big question mark there. And then a big old, however, you can't determine the form without the graph. Some kind of graph. You need some kind of graph. Or what College Board will do a lot of times is they will say something in the directions like assume the graph is linear or assume the association is linear. Okay. There's two more. S. Okay, so here's S. Difficult to calculate, but luckily the software, so it did it for you. Okay, so let's do this sentence. The typical distance between the points on the scatter plot and the least squares regression line is SY units. Okay, now this to me, what does this say to you? So the S for our starburst graph was 4 starbursts. This is a little tiny decimal. So what does that mean? Like, what does that actually mean in terms of the graph? Yeah, the scatter plot points are really, really tight against the line of best fit. And you noticed ours was not really tight against the line of best fit. That's why our standard deviation was so high. Is this helping? Okay. All right, last one, and we're going to do this one twice because we did not finish that yesterday. R squared, capital for some reason. Oh, hold on. Let's look at the recipe. R squared of the variability in y can be explained by a linear association with x. R squared percent of the variability in y is happiness. I think this might be a contrived math problem, by the way. I don't know about 40% of the variability in happiness being explained by not having math. I feel like this might be a problem that the textbook made up. I don't know. I mean, yeah, I guess. I do an awful lot of it though. Like, sorry, I got distracted and was. Okay, super important that you so that's we're sort of like just reviewed everything we've done in the chapter so far, right there. What did I write it wrong?
No, I just have a question.
Yes.
How do you know that R squared is a linear association for the correlation?
Oh, you can't actually. You can't. Let's just put that just to cover ourselves. It's an excellent question. I sort of took a leap by grabbing this regression output because I thought it was kind of hilarious. And also you most of the time you'll have a graph to look at. But that is an excellent question. Thank you so much for bringing that up. Okay, the last thing I want to talk about on this page is we will never use the things that say adjusted. We'll never use the standard error coefficient. Okay, so what I suggest is for my people out there who like to color their notes or highlight things, the only things that you need to look at in chapter 3 are those 4. If you could just narrow your focus to those 4 things, try not to get all confused by the rest of the numbers because we don't even use these 3. We will use these, but not till second semester. So I just want you guys to just seriously focus on those 4. And let me put this up again for a minute, just in case. Yes, honey. Oh, yeah. I would spend most of my note card on the recipe sentences. And the other part of it on calculator buttons. Yeah. And the last bit I would use on my note card is how to do DOFs properly, but I haven't taught that yet. Oh, actually, also, there's an algebra problem we're going to do in a minute. That's like, I know, I'm sorry. Okay, also, I think I mentioned, I have a Quizlet that someone made last year of all of the recipe stems with the sentences. Which I'm going to pick out. I just haven't even, I don't, am I done with sentences? I might be done. I'd like to be done. Okay, all right, so, again, we have three different topics today. That was the first one. It really wasn't a big deal. Mostly I wanted to review what we've done so far in the chapter, just to kind of like bring it back together, but using that software. But please listen, that'd be great. Okay, so you can shift that guy aside and get back to this. Okay, now we're gonna do some algebra. Okay, I know. Math 3 coming back in, here we go. Okay, so regression to the mean. Regression to the mean, I have to tell you, is old school. So, you know how like I was talking about how the 40-year-old accountant isn't going to be whipping his TI-84 out of his briefcase. You know who else wasn't whipping their TI-84 out of their briefcase? Like people in 1950. Like they didn't have one. I mean, I had one of the very earliest ones, and I was in the early 90s in high school, and it does everything that yours does now, except for like it didn't put the left, center, right in the inverse norm. But anyway, okay. But regression to the mean is an algebraic process to calculate the equation of the LSRL. Okay, do you guys know what that is? Least squares regression line. And that's the output that your calculator gives you when you do linear regression, a plus bx. An algebraic process to calculate the equation of the line of best fit, basically using R and the perfectly average point. Okay, and there's two formulas that you need that we're going to put in this spot. B equals R times the standard deviation of Y over the standard deviation of X. Y bar equals A plus B X bar. Okay, so write those two down and then we'll talk about what those are saying. So think back to your math one day. I know. What did you need to find the equation of a line? There's multiple correct answers here. 2 points, or slope and a point, or slope and y-intercept, but okay. That wasn't really anything, we just had to plug the things in. That was your favorite problems of all time. Anyway, okay, that is the case here too. So let's talk about like what this formula means. Standard deviation of y is changed in y. Standard deviation of x is changed in x. What do you know that is the change in y over the change in x? Slope. However, we're talking about a scatter plot, so you're saying times the percent of strength. So the percent of strength times the change in y over the change in x is how you find your slope. Like, hopefully you'll remember this, but you'll have to formula. Okay. Now, the other piece of information that you have to know is one of the great things about the least squares regression line is they all pass through the perfectly average point. What I mean by that is they pass through the point, the average of x, comma, the average of y. So if you average the x's and you average the y's, they will pass through that point. So you have a slope and a point, and you can find it algebraically. Okay, now what we've done, I've done some things to help you out by having you put that data in your calculator. So I want you to run two variable stats. Two variable stats. So stat calc, not one variable stats, but two variable stats. I just hit one variable stats. Stat calc, two variable stats. And then sell it. Okay. There's one piece missing from two variable stats, but luckily we have it on our paper. So what I want you guys to do is a couple of things. I want you to come here to the bottom of this. Okay, now do you see how the average of X is 18.0? We're just gonna call it 18. And the average of Y is down here, 23.8. So X bar comma Y bar. And this just means all of the X's were added together and divided by 30. And all of the Y's were added together and divided by 30. Okay, but I want you to actually see if this, I want you to look on the other side on the graph and see if this point is actually on the line. Because otherwise I'm just making up hogwash up here. $18, 23.8-ish. I mean, it's good enough, right? Okay, do you believe me that I'm not making up hogwash? I'm just not making up statistics over here at my desk willy-nilly. I don't know about that. I don't trust you, Mrs. Talbot. Okay. So first thing we need is R, which is 0.6. Do you guys know where I got that from? Shh. Do you know where I got R from? Do you know how to get R on your calculator? Linear regression, A plus BX. Okay. All right, now we need X bar, standard deviation of X, Y bar, standard deviation of Y. Those are all in the two variable stats we just got. So 18, 2.2, 23.8, 5.9. Okay, now I have to be honest and tell you that I hate that when people say that, and I just said it. But most of the time when you do a regression to the mean problem, they give you these 5 things and you just do the algebra. You don't have to do it based off of a table. Because why would you? Because the calculator will do this for you. But anyway, okay, so step 1, find the slope. Okay, so B equals 0.60 times the standard deviation of Y over the standard deviation of X. Also, when you're doing this process, you don't need to do parentheses or anything fancy. I just did 0.6 times the top divided by the bottom in one swoop. One fell swoop. Where's Matthew? I need Matthew. Do you guys know Matthew Bone? Yeah, he's my one fell swoop joke person. I actually saw him walking to school today. Weird. Okay, anyway. Okay, now hold on. I was expecting a little more excitement here. Thanks, Theo. Okay, anyway, then the next step is I'm gonna plug all that stuff into this second one, which is the perfectly average point equation, and find A, solve for A. I know that my math 3 students have a lot of practice solving for A. That is not true.
Yes.
No. This one might be slightly less satisfying. Unless I wrote it down wrong. Where's my discrepancy? I'm sure it's just rounding, but it's okay. It's fine. It's just, oh, the one from the calculator is definitely more accurate. This one, there's no rounding that happens here. It's like instant. This is like your technology answer. This is like your old school. I'm using the slide rule and the abacus answer here. Okay, anyway. Okay, that was thing number 2 we needed to learn. That wasn't too bad, right? Okay, now I have to tell you something interesting. I hesitate, I don't know. I hesitate to use our graph for this stuff. I'm not sure how good of a job our graph is going to do. The 5th period graph is much better, unfortunately. I think it might be because the size is smaller. I don't know. That's my view. But I feel like we should just give it a go. See what happens. I don't know, because I wanted you guys to use your real stuff, so it would mean more to you. Like that was the whole point. So I don't know. We'll give it a go. This is going to be slightly painful because I need to type in your things into your data into Desmos, and it won't let me copy and paste because it hates me. So I'm just going to need you to talk about your day again in a minute.
I love talking about my day.
Here I go. I'll look at the excitement on my.
And I feel like you can tell that. Yeah. Yeah. I just like the dollar.
Okay, you guys, hold on. Shh. I need your help. I need your help. Yeah, your help. I made a mistake. Okay, can you look at the pink table, please? Okay, so we're going down the Exodus. 15, 20.5, 19, 18, 18.5, 13, 20, 19.5, 16.5, 18.5, 18.5, 18. You're not helping. 21.5, 14.5. What? You're helping.
Wait, I thought we were looking at Exodus.
No, he just was ahead of us. We're good.
Oh.
Okay, we got it. Thank you. I just knew I typed a mistake. Shh. Thank you. Sorry about that. My bad. Okay. Thank you, honey. Appreciate it. Okay. I just knew that my slope and my wire number was a little bit off, so I knew I typed the number wrong. Okay, anyway, so if you're at home and fancy a scatter block and you don't feel like digging your TI-84 out of your briefcase, you could use Desmos. This, however, is a very specific one. I Googled Desmos linear regression calculator, not just the regular Desmos calculator. And it will have a table there for you, which you cannot copy and paste it to. Very upsetting. Okay. It says our slope is 1.58 something, our y intercept is negative 4.8, r squared is 0.36, r is 0.6. Does that make sense to everybody? Okay. Okay. So just so you know, that's out there for you. That's not why we did this. We need to talk about the last thing for this lesson, which is 3 definitions. They're actually all kind of the same thing. But I want to talk about that in terms of your particular data. So I wanted this up here. Shh. Okay, high leverage point. The definition of a high leverage point is a point that has a relatively high or low X value compared to the other points. A high leverage point is a point that has a relatively high or low X value compared to the other points. Okay, so we're going to start with that definition. Okay, so you're a 40-year-old accountant right now, and you have some theory about something in your sales or marketing or whatever, and so you made this scatter plot of sales over certain months, blah, 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 blah. And in your data, it's a little bit hard, but the points that are most to the left and most to the right would be called high leverage. I want to have a 60-second conversation about why that makes sense in terms of the word, just the word high leverage. What's leverage? Yeah. Importance, like whether or not it like helps you make a decision. It's like how important it is, high importance. And the reason is because those points help you see if you've got a pattern or if your theory is true or not true. If you've got a point down here, like let's say, and it's right against the line, you're like, yes, my theory was right, because even when I go farther down the x-axis, my pattern's still holding. If you have a high leverage point that's like here, way off, then you know my theories need work. I need to fine tune the situation, or I'm not really right about what I was thinking, which is bad, sadly, when you're doing research. But anyway, so high leverage means like high decision making. It's helping you decide. Okay, so coming in here, super high leverage, high leverage, medium, not really so interesting, more high leverage, super high leverage again. Does that make sense? So the ones on the outside are the ones that are really going to help you decide whether or not you've got a really good pattern. Okay, so that's a high leverage. Okay, what do you think outlier means? That's an easy one. So we're going to say a point off of the pattern with a large residual. High leverage points and outliers are both examples of influential points. That's not the definition of an influential point, but they are both influential points. And the definition is a point, if removed, and now you're going to be able to see why I wanted to do this on Desmos. A point, if removed, affects slope, y-intercept, r, s, or r squared. So any point where you took it out and it would change all of your statistics or the way that it looks is called an influential point. Okay, so the last thing we're going to do when you're done here, we're just going to try to pick. This is going to be hard for us. That's why I didn't really love our data, but like take a look at fifth periods. Okay, do you see this guy? Like he's a perfect example of a high leverage point, like whoever this person is. I think I have the biggest residual. This is me. Whoopsie. So maybe this one, we might be close to the same, but anyway, so I'm gonna talk about in that class, what would happen if I removed this point and what would happen if I removed my point, which is an easier conversation than ours. So let's go back to Desmos. Actually, why don't we look at our actual graph real quick up here first? Because Desmos kind of lumps them together. I think I can actually change the scale. Actually, I can't because this graph is Desmos that is a printed, so I must have been able to do it at some point. Okay, okay, so there's an obvious, I'm so sorry. Evan, there's an obvious one that we can take a look at by taking Evan off. Which, by the way, not to like blow you up, but he did say that he did not stretch his hammer down all the way, which might explain the outlier in this. That might be actually more like down the. He still picked up a heck of a lot of starburst, don't get me wrong, like, there's still a lot of starburst to have. For high leverage though, I really wanted to take, let's just take this guy off and see what happens. So that's why I wanted to do this on Desmos. It's really easy to take a point off and put it right down. And look at the summary stats. Okay. So. Okay, so we decided point one was going to be Evan, which was 19.540. Who was the point that was this on the furthest to the right, left on the x-axis? Mariana, is that you? $13, $18. Okay. Okay, so all we're gonna do from here is we're just gonna go back to Desmos and we're gonna see what happens when we take those points out, but we're gonna look at very specific things. Okay, for S, we're just gonna have to use common sense. And then don't let me forget, we need to write that R squared interpretation on here on the pink page from yesterday that I didn't have time to do. And then we're done. Okay. So first question I have for you, Evan's point. This is a really hard question. Is it high leverage or an outlier? Outlier. Okay. Okay. So that's an outlier. Okay, so we're going to go to Desmos and see what happens when we take it out. Oh no. Oh no. How do I take it out?
This is trying to make it extra complicated.
I know. It hates me. Desmos hates me. Okay, what was it again? 19.540? Okay, so what if I made this okay, so I flip-flopped two of them. Did that work? Yeah, it worked. Okay. Okay, so this is really tiny, so I'm gonna read it to you. The first thing was A, correct? Okay, so A went to negative 2.6. Negative 2.6. Okay, so right, A equals negative 2.6. You know what I'm talking about? Yeah. Okay, what was A before? -5 or -4.8, somewhere around in there. Okay, so what happened to A? Increased. Okay, the slope is 1.4, so put B equals 1.4. What happened to the slope? Decreased. Okay, so what I really want you to think about is our line was kind of like this, and then it tipped up. It went up on this side and got a little bit flatter. It tipped this way. Okay, and I want you to put a note here. You can't see it. Thank you. Outliers pull the least squares regression line toward them. So since it was a high outlier, that side of the line was pulled high. Okay, R is 0.63. And R squared is 0.40. R was 0.63 and R squared is 0.40. What does that mean? What happened to those? They increased. Why? What happens if you take an outlier out? Yeah, stronger association. Okay, now for S, it doesn't calculate S, but let's just use common sense. That one had a really huge residual and we took it out. So the average of the residuals is going to go down. Yeah. And these two pieces of information jive with each other. They both mean stronger association. Okay, now the wild card is taking out 13, 18. I don't know what's gonna happen. Okay, so I'm gonna go back in. I added Evan back. Now I'm gonna take out Mariana, but I'm gonna put Evan in that spot. Okay. So I took out Mariana. Slope. Start with actually A. Y-intercept is negative 6.6. Slope is 1.7. Hold on, I'm just gonna copy this off of here. Okay. All right, there you go. You can have big numbers instead of tiny numbers. Almost done. What happened to this to the y-intercept? Decreased. The slope went up a tiny. R and R squared went down, but just the tiniest bit. But we knew that was going to be the case because she wasn't really that far down the x-axis. Okay, so if it's a weaker association because these went down, then the amount of error will increase. It kind of worked. It should be a lot more drastic if it's farther down the x-axis, but it's okay. Last thing, if you guys could grab your pink sheet, I just want to write that sentence from yesterday and then we're done. Just a heads up, on Friday and Monday, we're doing logarithms, so yeah. All you really need to know is where the log button and the E button are on the calculator, like log and natural log and E. Okay. R squared interpretation. Let's find the thing. Okay. R squared percent of the variability in Y can be explained by a linear association with X. And again, ours, we're just pretending that our graph is linear-ish. Okay, 36% of the variability in number of starbursts Okay, so 36% of the variability in the number of starbursts you can pick up can be explained by a linear association with handling. The rest of that is not really like part of the interpretation. It's just fun to think about. 64% is something else, like grip strength or what did I say? Palm size? What else did you guys say that was cool? Oh yeah, fingernails. Oh yeah, speed, technique, Squidward, technique. Yeah, anyway, 64% is other variables. Somebody in fifth period yesterday, super cool person, asked me if there was a way that I could make scatter plots enough to figure out exactly what would add it up to 100% of all the things. And I was like, I don't know, it sounds like somebody's life's work. Okay. Not for Mrs. Talbot. Too lazy. I got way too many Netflix shows to watch for that. Also, I owe you 3 jokes, I believe. 3. Did I show you the duck one? Okay. All right. This was from 2 nights ago. You have a guy and his girlfriend, and he says, I think we should give it another shot. And she says, we should break up and I can submit. And she makes a graph of their relationship, the downward trend. And he says, huh? And he says, maybe you're right. And she says, I knew data was to use you. And he said, no, I think just think I can do better than someone who doesn't label her as. This one says, holy shit, and look at this. Study finds 50% of people bored by statistics. Do you see why that's funny? Because the one guy's excited and the one guy's not, it's 50%. Okay. Here's today's. It says, out, liar. And he says, your theory is wrong. I like that one.